Okay, let's actually begin. So, I have your tests to give back. I'll give those back at the end though, so just remind me. I want you to be distracted looking through them while we're doing some learning up here. Next topic we are going to do is linear approximation. This was also one of the bonus problems on the test, so if you don't know how to do that, didn't know how to do that problem, now you're going to know how to do it. Linear approximation. And we're going to also talk about something called marginal functions. So, two different things. Your textbook puts it into one section, though I think it's 3.5, but don't quote me on that. Two completely different things. Okay, so let's start with linear approximation. And the gist of this here is using the tangent line, which is a linear function, to approximate the outputs of an original function. And the idea is the following. Okay, so, boom, boom. So you have some function doing its thing. Your function there. And let's say you know about some point on this function. You know what the function is doing at this point. So there is this point, let's call it A, and of course the corresponding y value will be f of A. So you know this function, you know what it's doing at A, you know what it's doing at A, the output is going to be f of A. So the idea is there is some other point of interest, let's call it over here, call that guy the x, right? So this might be some point of interest that might change over time. Okay? So now the corresponding value for that is going to be f of x. Now, for some reasons, perhaps because this part of the function doesn't exist, or for whatever reason, calculating f of x is actually difficult. And I'll mention some scenarios in which that is actually difficult. But I know what's going on when my input is a, but when my input is this x value, I might not know what's actually going on. So the idea here is, let's actually use a tangent line to in the following way. So I can, because I know this coordinate, and let's say I also know enough to get a tangent line going through that point. Now the equation of that tangent line is going to be something that's actually well known, right? So if you go over here, the equation so, right, recall how to find the equation of a tangent line. So if the point is x1, y1 equals a comma f of a, so that's the input and output, and you know that the slope is just going to be, of course, the derivative evaluated at a, then you could use y minus y1 equals n x minus x1. This would be y minus f of a equals f prime of a times x minus a, and so you get your y for the tangent line is actually going to be equal to f of a plus f prime of a times x minus a. So that's going to be the equation of this line right here. So this is y equals f of a plus f prime of a times x minus a. So now here, let's just do some notation. We are going to measure things in terms of the difference. So I know the output f of a. the difference between f of a and the new y value, we tend to call that delta y. Of course, the difference in x values, we tend to call that delta x. Now, let's suppose we don't want to use the original function because it's complicated for some reason. So we are instead going to use the corresponding y from the tangent line to actually approximate the curve. Now the distance between that is what we call dy, as in the numerator of the Leibniz notation for the derivative. And now, here's the idea. When these guys are very close, you'll notice that the differences between these two are actually going to be very small. The closer we are to, the closer x moves to a, the difference between the tangent line and the function are going to get smaller, right? That's what a tangent line actually does. So it turns out there are going to be situations in which the change in the derivative is going to be very close to the change in the original function. Now, measuring the change in the derivative is going to be easy. Why is it easy? Because it's just the equation of a straight line. I can talk about how a straight line moves very easily, whereas the function itself might be very complicated. I might not be able to get a handle on that function itself. So what I can use then is I can use dy to approximate the delta y, because when these two guys are close, those two guys are almost the same thing. The difference between the two is going to be very small. So from this, we'll know that the f of x will be approximately equal to the y of the tangent when x is close to a, right? And the closer you can get, the more these two guys will start to align. So my original function is going to behave like the equation of the tangent line at x when my x gets close to this original reference point that I have. And so, in other words, I can say that my f of x is approximately equal to f of a plus f prime of a times x minus a when x is near a. This is an important formula. It's called the linear approximation formula. That's where the title comes from. Linear approximation is using the tangent line to approximate what a function is doing, and to do so, we use this actual formula. Now, what I want to do is I want to actually just go through a couple silly examples for you to see this formula in action, and then we'll probably move on to the next topic. So the kind of question that I would ask you here would be exactly the kind of question that I asked at the bonus. I'm going to give you some function or some value that you want to approximate, and you're going to use this formula to get some sort of approximation to that answer. So let's do an example. Use linear approximation to estimate what is the square root of 3.99. So we're going to use this formula. We're going to walk through an approximation for that value. Here's how we're going to do it. First of all, what we want to do is we want to be able to use this equation, which means we're going to need to set up a function to measure something that we care about. Now, I want to actually approximate the square root of 3.99, so it makes sense that the square root function is probably the function that I want to concern myself with here. So I'm going to set f to be the square root of x, and I want you to notice that we want f evaluated at 3.99. Okay? Now, for the purposes of this example, we will consider that to be complicated. That's not something we can get a handle on because I don't know off the top of my head what that value actually is. So the goal is here is we're going to take this x to be 3.99, and we need an a close to x for which we know all the values, for which we know what would the output of the function be at that value, and what would the derivative of the function be at that value. So, can you think of a number that's super close to 3.99 for which we know what the square root of that value is? 16. No. 4. 4 is something that's super close to 3.99. There are other things for which we know exactly what the square root is. We know what the square root of 1 is, we know what the square root of 16 is, what 36 is. But of course, for this to work best, they need to be close together. So I need to think of the closest thing to 3.99 that I can get. 4 is a pretty good candidate. I would actually know everything here. So what I would do is I would take x to be 3.99 and set a to be 4. Then, if your f of x is the square root of x, this means that your f of a would be f of 4, which would be the square root of 4, which is 2. And your f prime of x, which by now we should know that's 1 over 2 radical x. This means that your f prime at a is just going to be f prime at 4, which is 1 over 2 radical 4, which is a quarter. And so now, we can plug into our formula. I know that my f of x is going to be approximately equal to f of a plus f prime of a times x minus a. That's a new formula that we need to know now, so every time we use it, we should write it down. And so, this means the square root of 3.99. That's just f of 3.99. This is approximated by f of 4 plus f prime of 4 times 3.99 minus 4. And then I'm going to plug all those guys in. So this means the square root of 3.99 is approximately, well, it's going to be f of 4, which is 2, plus f prime of 4, which is a quarter, times 3.99 minus 4, which is minus 0.01, which we can write that as minus 1 over 100. So it's 2 minus 1 over 400, which is 799 over 400. So the square root of 3.99, I don't know what that is exactly, but using a tangent line, using a linear approximation, my guess for what that is would actually be 799 over 400. Now, just for fun, let's actually see what would that actually give me. If I take 799 divided by 400. So this is actually 1.975. So that's the decimal version of that number. Now, compared to, let's look at the actual answer. What is the square root? So I'm going to use my calculator now to do 3.99. And what is actually the answer? The actual answer? It's 1.9. So far, so good. 9. So far, so good. 7. We're right up to 3 decimal places. This is amazing. 4. We messed up here. But the next number is actually a 9. Meaning, with rounding, if I rounded, I'm actually correct in my guess up to 4 decimal places. Right? Look, Mom, no hands, no calculators. Like I did this without a calculator, right? So that kind of tells you how much a tangent line can simplify the problem. Now, of course, this is a very simple problem, silly problem. If you had to figure out what the square root of 3.9, of course you just plug it in your calculator. No one's going to do this. That's not the point of this exercise. The point is to show you how close I could get without being able to actually deal with the original function. Instead of dealing with the square root function, I was able to deal with this equation, the equation of a line, right? And it got me pretty darn close to what the actual function would have given me, right? So that just shows you in principle why something like this will be powerful and how it's actually used, is that sometimes functions are very complicated. Now, one way in which this is used that is pretty cool, that you can't just plug into your calculator, right, is that there are times when functions are complicated in the sense that they don't even exist, right? So let's say you're measuring something over time, and blah, 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 stuff is going on, and boom, you're here, and this is the present, right? But you want to be able to predict, where do you think the function is going to go next, right? So you don't know, is the function going to go up, is it going to go to the middle, is it going to go down, what is going to be the behavior in the future? You see, it's all an unknown, right? So it turns out we simply live in a reality where things don't actually drastically, so yes, we have examples of functions that like shoot off to infinity and do all sorts of crazy things. But it turns out that in real life, that rarely ever happens. Functions will tend to kind of not deviate too far from what they're currently doing in general, right? So the only thing that would cause some kind of crazy deviation that's like totally off the charts would be like a catastrophe, right? So it's like, you know, a solar flare from the sun heats something up, right? Like catastrophe is usually what would cause some kind of crazy spike. But in general, how your function is currently behaving, the direction in which it's currently going in, which the slope of the tangent line will tell you about, kind of can tell you how things would actually end up. So it's kind of like when over here, what we're actually doing is we're looking at the square root function, which looks like this, right? Now, well, this is kind of going back into the past. We'll actually do one where it goes into the future. At 4, I know what's going on, but could I have predicted where this was coming from a little before? And the answer is, yeah, I would have predicted that that's what the value was coming from, right? I'm going to actually do one where we go into the future pretty soon. And it turns out that you can actually use this kind of analysis to actually talk about and predict what a function is going to do when you don't know what the function is going to do, right? That's as complicated as it gets. I don't even have a rule to know what's going to happen. But what you can do here is if you understand how things are behaving here, and you can kind of figure out a tangent line at this point, and let's say I wanted to know what's going on at this point in time, what I would do is I would guess that it's going to be here. Now, the closer we are it turns out the better my approximation is going to be. So I don't know what the function is doing, but erecting a tangent line here, I can just use the point on the tangent line to predict, you know what, I don't know what the function is going to do, but I'm going to guess it's going to be here at this point in time. And yeah, you can actually use this kind of analysis to do that, and it is actually used this way. And in case you might think, well, there's no way that actually works out in real life, does it? Well, Goldman Sachs makes billions of dollars with this kind of technology, right? So if you're watching a stock, right, very erratic function, right? Like you're watching some kind of stock, and it's usually very spiky. Like that's a stock, right? And Goldman Sachs wants to know, is the price going to go up or is it going to go down? And are we going to buy, are we going to sell, are we going to short, what are we going to do in the future? Well, I don't know what's going to be in the future. But the thing is, far into the future, they can't tell. They wouldn't be able to tell what the stock is going to do tomorrow. But you know what? What is it going to do 1 second from now? That's a different question. That's not a very far jump to make. So what we can do is figure out some sort of way to approximate the trajectory, the current trajectory. So what they can do is somehow get some calculus in here, get a tangent line, and they're like, you know what, I don't know what's going to do an hour from now. That window is too far. Remember, for the approximation to work, it has to be very close. So they'll like predict 1 second from now, half a second from now, right? A quarter of a second from now. Now, a human being might not be able to do much in that time, but you have a supercomputer who's doing the trading for you. A supercomputer in 1 second can make millions of trades. They can buy and sell millions of stocks, right? So basically, they have a model that says, and it uses a lot of calculus in it, that says, okay, you see a stock doing this, here's where we predict it will be a half a second from now. If this is the trajectory, do that, right? Now, they are going to be wrong. They can't predict the future, but they're going to be right enough to make a profit. Sure, they're going to lose some money on the dollar in the 4th decimal place of the cent value of the stock, but they were right all the way up to here. So they'll make millions of dollars and lose a couple $100,000. At the end of the day, they're ahead millions of dollars, right? So this is the kind of idea that they would kind of go into using, right? This is one of the main uses of calculus is linear approximation. How do you predict what something is about to do based on what it's currently doing, right? Essentially kind of try to set up a calculus situation on the current situation and then use the tangent line to predict what's going to happen. Now, it's not a very good indicator for far into the future, but when things are close, your delta y and your dy are super close. And so you can actually make a prediction. And if you have the machinery to pull it off, that prediction can help you get in a good spot. So that's one way in which you could actually use. So I mean, it's kind of silly of me telling you about, just plug that in your calculator, right? In real life, it's a little bit more complicated than that, but the idea that we used here can pay dividends, pardon the pun, in many ways. That was just one example of how we can actually use this. So what I want you guys to do now is to actually do this for another problem. I'm going to ask you guys to estimate the cube root of 8.01. Okay, so I want you to go through this process and actually do that. You guys 5 minutes.
is 8.01, then I set a to equal to 8.
Okay,
And then I found f of a, which was,
what is f? What is f?
oh, okay, well f of x is equal to the cube root of x, which
Right,
is set to
so
equal
that's
to-
the first thing we want to do. So one, you want to set up function. So you here f of x equals the cube root of x seems like a smart choice. And two, you mentioned that you would you found your x and your a. So that's the next thing. So you said your x is equal to the actual value that you want, and your a is something close to that, which you chose 8. So this, what you should know is x is the actual value you care about. A is a value close to x that you know, or at least you can find easily, all the info for. Okay. Then we went into the situation of where you wanted to find your f of a and your f prime of a. Okay, so now I'm picking up there. What was your f of a?
Me?
Yeah.
Oh, f of a was the cube root of 8.
Right, so that's just f of 8, which is the cube root of 8, which is 2. Then?
And then I found f prime of a. Well, I found f prime of x first.
Right, what is f prime?
It will be x to the 1/3, so then it's 1/3, 1 over, I don't know if this is right, to be honest, 1 over.
Just give me the power rule version. Right, so you can think of this as x to the
1/3 x to the negative 2/3.
Right, x to the negative 2/3. If you wanted to write that in radical form, it would look like the cube root of x squared. That's what it would look like. Or it's nicer to find the cube root of x and then square that. It's going to be the same thing. And so now, if you want to find your f prime of a, well, that's just f prime of 8. That's going to be 1 over 3 times the cube root of 8 squared. Cube root of 8 is 2. You square that, you get 4. Multiply by 3, you get 12. So that's 1/12. And now what? Did you get 1/12?
Yeah.
No? So okay, so you probably made a mistake in the switch here, but it's 1 over 12.
I did the. Okay.
Yeah, it should be 1/12.
I don't know what happened here.
Yeah, so computational error there, try to figure out what happened. But what would you have done after that?
And then I would have done the equation, worked out the equation.
Right, so at this point you plug into linear approximation formula. So this is where your f of x is approximately equal to f of a plus f prime of a times x minus a. Or in other words, if you look at your f of 8.01, it's going to be approximately equal to f of 8 plus f prime evaluated at 8 times 8.01 minus 8. So that is going to be 2 plus 1 over 12 times 0.01, which is 1 over 100. 2 plus 1 over, this is 1200. So 2 I can think of as 2400 over 1200, so this is 2401 over 1200. So that would be the guess. Let's do the comparison. By the way, this guy is, now of course, this comparison part you won't be able to do on a test because you won't have a calculator, but this is just for fun. This is actually 2401 divided by 1200. It's 2.00083, and I think the 3 is just repeated. Now, if you look at the actual answer, actual answer, you take the cube root of 8.01, that is going to be, don't have the cube root here, so 8.01 raised to the 1/3. So the actual answer is 2.000. Okay, so far so good. 8. We're good up to 4 decimal places. 3. We're good up to 5 decimal places. 2. 9. However, if we rounded, that's 6 decimal places. But we have 5 decimal places solid. Like without a calculator, I know what the cube root of 8.01 is up to 5 decimal places. And this is actually one of those situations where technically you've predicted the future. So your cube root function is going to be increasing at that. So the thing is, you know what it is at 8. It's 2. But now you're like, what is it going to do over here at 8.01? Right? So, I mean, your cube root function goes like that. So. And so you don't know what the function is going to be doing in a little to the future, but with a tangent line, you would guess that the output is going to be 2.000833, and you'd be correct up to like 5 or 6 decimal places, depending on whether you want to take the rounding with you. So I think that's pretty cool. Yeah.
How far apart can the A value and the X value be?
As close as you can possibly get. So in this class, I'm going to give you suggestive values, right? So it's like, I can ask you about like the square root of 15.99, where 16 would be the obvious guess, or you know, for 8.01, 8 was the obvious guess. In general, the closer the better is the answer to that. But of course, for stuff I can give you in a test that you'd have to do by hand, what I ask you about is going to be very suggestive. It's going to be things that you, oh yeah, I know what the actual answer is. Yeah, so the problem type is going to look something like this. I'm going to tell you, approximate this random number. And you're going to say, well, I know about this number. And you can use linear approximation to do the approximation. But as close as possible is even better. And there are ways to get even closer than what we did here, but that's not in our syllabus, so we're not talking about that. I think we'll wrap up there. So linear approximation, that's another topic. And I have your test to give back, and we'll pick up with the marginal functions stuff on next class. So, see you guys tomorrow.